is the linear velocity and the linear acceleration at point B. So at point A, we found our velocity is given omega times ROA, 1 times 100, that's the 100 millimeter per second. And now using relative motion relationship vectorally, we can write the velocity at point B equals velocity at point A plus B relative to A. And that is the equation we have written. VB, velocity at point B equals velocity at point A plus velocity VBA. It is a vector equation. It is not arithmetic sum. It is a vector equation. And the relative motion you also learn in your engineering dynamics course, because there was a little subtopic relative motion. And one of the biggest application of the relative motion is the machinery, synthesis of mechanism, and the other application is a very well known. It is the air traffic control. Air traffic control, we use relative motion there. And before computerization, they used to use ruler in the control tower. They used to use ruler to determine the two aircraft distance from the control tower and what is the relative distance between them. And subsequently, they can also calculate the velocity. So this principle we learned in our engineering. So maybe I quickly explain to you the relative motion from where it comes. So it is consider that we have a air traffic control in Singapore Changi Airport here at that point. And you know, all the aircraft, when they are very close to Changi Airport, they always contact with the air traffic controller, and they also air traffic controller asks them, "Hey, what is your identification?" So that aircraft say, "My number is that, or whatever it is, my flight number." And then the other aircraft they also see, and then they also ask one thing: which is your coordination? Because in the cockpit pilot can see what is the latitude, what is the longitude. And so this way, air traffic controller understands where is the location and what is the distance between the two aircraft. Clear to everyone? And this way, and if they are very close, then they give the instruction that you have to be a little bit apart, or they are very far, they are away from the main path, then they also give the instruction. So for example, if we have two aircraft here, I see some very here, that's good. So if you consider that one aircraft is here, aircraft A, and the aircraft B is say somewhere here, and this is aircraft B. So and this is air traffic control here, and the air traffic control asks aircraft A, "What is your position?" So aircraft, they look at their own equipment or the things that is in front, displays and equipment in front of them. Based on that, they can say latitude and longitude. And when they say latitude and longitude, the air traffic control can know where it is. So for example, based on that, consider the distance of the aircraft A, a little bit offset. The shortest possible distance is, say, this one is RA. The shortest possible distance up to this point. And then the air traffic controller also asks aircraft B, what is the distance or the coordination? Then the air traffic controller calculate the shortest possible distance is a RB. And these things used to do on a map. Air traffic controller used to have, before the computer, they used to have a map, and they used to have a ruler. And they also have an angle or all these things they can easily calculate. So they have to compass, all these things. Because when I did my undergraduate course, we used to do this way. We did not have a computer system. So if a air traffic controller, we used to ask them what is their distance, or the coordination, and then we calculated the map, and then we can calculate how far they are. And another thing, very important, that is, what is the relative distance between them? That distance. And that distance is called RB relative to A. RB relative to A. So now that's all distance in kilometer or meter, whatever you want to say, or feet. So we can write vectorally the RB equals RA plus RB relative to A, and that is the distance equation vector form. Distance, and distance is a meter or kilometer, whatever it is. It is a distance equation. And now have a look. If I divide by the time d by dt, the whole equation on both right hand side and left hand side, then it becomes RA plus RB relative to A, and then this is now, look at here, this one I am divided by the time, and then I get VB, the velocity of aircraft B, and here is the velocity of aircraft A, and here is the relative velocity of aircraft B relative to aircraft A. And it is now, because that was a meter and the time was a second, it becomes meter per second or kilometer per second, depending on what is the distance you put. Clear to everyone? And then if you differentiate this equation again, the dV by dt, and then you put a VB here, and then here dV by dt, and you put here VA plus VBA, and that become now, you differentiate your velocity again with the time, it become now acceleration. It become now acceleration AB equals AA plus AB relative to A. Now look at here very carefully, young people. It is a vector equation. It is not a arithmetic sum. Okay, so if you know this value is a 2, say this value is a 2 meter per second square, and this is a 1 meter per second square, and this is a 2 meter per second square, you cannot sum them up because it's a vector equation. Clear? And that is meter per second square or kilometer per hour square or whatever it is, or kilometer per second square. It's depending on, this is, we call it relative motion. And this relative motion in a vector form we utilize in air traffic control. That's the biggest application. And this one, what they do now is a computerized, pre-programmed, but the equation is still the same. Clear? So still the air traffic controller, they ask the air traffic what is the coordinates, and they put these coordinates into the computer, and computer calculate all these things. Clear to everyone? So it is human calculation, and now this is also we used in our machinery here. Look at here what we did. The velocity at point B equals velocity at point A plus B relative to A in a vector form. That's how we are saying using relative motion, because that relationship is coming from that equation here, which I showed you here. Clear to everyone? That is the origin from where you get, and you learn that things in your engineering dynamics when you started your program. Clear? And now the only problem is in this equation we do not know its value. We do not know its value either. So we have one equation. First of all, it is a complex equation. It is not an arithmetic sum. Second, it is a vector equation. Second thing is, we do not know its value. We do not know its value. How can we get this value? Even mathematically, we call it statistically undetermined. You have one equation, two unknown. If you have one equation, one unknown, you can still solve it if it is a linear equation. But here, complex equation, because it is a vector equation, and then also two unknown. So our life is really complicated and really become complex here. So the graphical method comes here to help you. In graphical method, although two unknown, vector equation, still we can solve it. But arithmetically we cannot solve it. Arithmetically we cannot solve it because two equation, here two unknown, VBA and VB, one unknown, and then on the top of it, it is a complex equation because it is a vector equation. So therefore we cannot solve it. Only graphically we can solve it. There is no other way. And graphically way, one of the important thing is, in graphical way, we need to know few rules. Those rules, I think I wrote it for you, but I'm not sure in Canvas it is very clearly shown. But I actually wrote here for you nicely with my caricature writing. I believe that you will be able to read it. The first thing, draw the mechanism in scale. That is the first thing you have to do. Position them correctly, that is. Select an appropriate scale for velocity vector. And also your acceleration as well, not only velocity. And then, interesting thing, select an origin of the vector polygon. Unfortunately, when I chopped it, when I scanned it, I chopped it, the polygon, here's the N here. And the most important thing is start from number 4. Direction of all parameters must be known. Must be, the word must be, not should. Direction of all parameters must be known. That is, every component of the velocity, every component of the acceleration. Direction must be known to us. If not, we cannot solve graphically. I'll come in a second about that. And then, magnitudes or value of some parameter should be known. Here the word I use should, not must. You understand the difference of the English word. Some parameters value should be known. Not all, some. Okay? And then I said, links that have connection, number 6, also very important. Links that have connection with ground, their velocities and acceleration should start from the origin of the vector polygon. I will come in a second. Which link has a connection with ground will come in a second to identify it. So links that have connection with ground, their velocities and acceleration should start from the origin of the vector polygon. It means origin, it means starting point of the drawing. Starting point of the drawing of the vector polygon. Clear to everyone? I will be coming to that point. We'll be going through it. All absolute velocity. Here another important thing. Number 6, I said links that have connection with ground, their velocities and acceleration should start from the origin of the vector polygon. And number 7, I said all absolute velocities and acceleration, that is one letter index, they should also start from the origin of the vector polygon. Very important. All absolute velocities and acceleration which has one letter index. I'll show you in a second what is one letter index mean. Their velocities and acceleration, those velocities and acceleration should also start from the origin of the vector polygon. That's the things, yeah, with one letter index. Number 8, all normal components of the acceleration, all number component of the acceleration must be known. Their values, in bit values must be known. Must word I use 2 times. Direction of all components, the velocity and acceleration must be known, and the magnitude or the value of normal components must be known. 2 cases I use must word. And then some parameters, particularly some tangential component parameters values should be known as well. Because when you use normal and the acceleration, we use the coordinate system of the normal and tangential coordinate system. You learn 3 coordinate system for the particles or the rigid body that undergoes a curvilinear path, a path which is not a straight line. You have to use one of the 3 coordinate systems. One is the rectangular coordinate system. An example is a projectile motion, and you know at the moment the largest after the Second World War, or maybe even not the Second World War. So the Second World War was not as intensive as the war is going on between Ukraine and Russia. Because in one day, if you launch more than 60,000 projectiles, no country in the world can have enough projectiles to have a 2 years or 3 years long war. No country in the world, except Russia. Because the total worlds, combinedly how many projectiles they manufacture, Russia can manufacture more than that. After the collapse of Soviet Union, its defense industry was not privatized. It was still under the state. So that is the things at the war is going. You will see the whole NATO and all countries, they are pumping their everything, but still they can do anything. This is the main reason. But most important thing is, in projectile motion, you need to use our rectangular coordinate system that you learned in your engineering dynamics course. So if projectile does not go to the rail target, your equation is wrong. There are 7 equations, 3 equations for the vertical direction from the ground to the maximum height, and then 3 equations from the maximum height to the ground. So 6 equations there, and 1 equation is a range. These 7 equations are the fundamental equations in all projectile motion. So this projectile motion, if the projectile, your projectile does not go to the target, it hits the civilian people, then therefore it will be investigation, and usually all the coordinates calculated by engineers in the uniform of army, and one of you will be there, for example. Okay, so the engineer will be held responsible that why the projectile is not going to the right target. It means projectile engineer did not learn his projectile motion as a rectangular coordinate system when he did the dynamics. That is the whole thing is coming. Clear to everyone? So it's very important. But projectile motion we use not only for the bad purpose like war, we also use for good purpose. For example, we drop food in the flood affected area or some area. Some people are, we cannot evacuate them, but we want to drop food. But we want to drop food such a way so that people can get it in the right place, not fall somewhere else. So from the plane or from the helicopter, when you draw, you also need to calculate where the projectile will fall, food will fall. Clear? So therefore, good purpose as well we do. Which is no. So, but all engineers do based on your projectile motion, which you did in dynamics course. But I'm not sure how much you actually at the time teacher told you all these things, but this is the fact. Okay, so you use projectile motion as a part of the normal and not normal, rectangular coordinate system, and we also use normal and tangential coordinate system as well. But that is mainly we use in the design of the curve path. In the, that you go sometimes drive 100 kilometers, there is a little curve, right? So you need to make sure that 100 kilometers people can go if they cannot skid from the road. So again, although you think it is a civil engineer job, but actually it is not a civil engineer job, because all the dynamics problem, projectile motion, and the curvilinear path is designed by the mechanical engineer. Okay, they are telling you what should, because civil engineer doesn't know these things. Civil engineer doesn't know dynamics because they don't go through it. So therefore, the road design, when you put the curvature, it be done by the mechanical engineer. That's why mechanical engineers is a really, really very big, wide area. They can be everywhere. Where the civil engineer works, they can be there. Many of you don't know, in a power plant, that power plant, the power station where the electricity is generated? Any one of you have any idea? There is a lot of engineers work. What percentage of engineers from which program is coming? Any idea? 85% from mechanical. Any power plant in the world. 85%. If you have say 1,000 engineers, 850 engineers will be mechanical engineers in a power plant. Many of you think all will be electrical engineer, but no, electrical engineer less than 15%, around 10%. Clear to everyone? So your scope is very big because you are doing many things. That's what I'm saying. So now, normal and tangential coordinate system we use, and also we use in machinery, like our synthesis of mechanism. And then you have another coordinate system we call cylindrical coordinate system. It's a 3D problem, but if it is a 2D problem, then it is a polar coordinate system. And cylindrical coordinate system, one of the example is in Singapore. So if you have a multi-story car park, so when you go the ramp, you design the ramp, and that ramp need to be designed by mechanical engineer. It cannot be designed by civil engineer. Civil engineer will be only looking at the concrete part. If it is the ramp is designed by metal, then civil engineer not needed at all. Because the metallic structure, our mechanical engineer, they know very well, because they do as a part of the solid mechanics course. Clear to everyone? Only if the concrete, you are putting the concrete strength, maybe you don't know very well, so that's why you need a civil engineers. But otherwise, it is your job. Clear? That how tightly the radius will be developed so that car can go at a particular speed without hitting the wall. And also it has enough radius to move. So all these things is dynamics. Many of you do not even realize that how much you use the dynamics in your real life. I cannot even imagine. When I go, I even come to this room, I walk from the hotel here, I can see everywhere dynamics. Because that's the vast area. So now, we use 3 coordinate system. We are not using cylindrical coordinate system or polar coordinate system in our this course, but we use normal and tangential coordinate system for acceleration, and also we use partly rectangular coordinate system in your assignment. In your assignment, you also use rectangular coordinate system because all the velocity you put in horizontal direction vx and vy. So that is your, and also your imaginary value in the y direction is actually vy or va or aoy, and the horizontal direction is your real value in the x direction. So that is your ax or bx. Clear to everyone? So now these are the things you need to remember, but you don't need to memorize them because you will forget. But the one thing is, when you do a lot of problems, these things will come to your head automatically. But I put them nicely here so that in the future reference you keep it there, because you will not find them so nicely written in the book, even including that beautiful book which I showed you, the Norton's book. No, it is not there. So it is coming Firoz Alam's head, as Firoz Alam learned long time ago when many of you are not even born. Clear to everyone? Do not throw it away. It is very vital things. Okay, so we will be using these things. So now look at here very carefully. Number 4, direction of all parameters must be known. Some parameters value should be known. That's the beautiful word. Let's go to have a look now. Go back to our problem 1. Here we have 3 parameters. We have a BB, we have a VA, we have BBA. All 3 parameter direction must be known to us. Otherwise, we cannot do graphically this problem. That's the one thing. And then it says that links that have connection with ground, their velocities or acceleration should start from the origin of the vector polygon. Now let's go to have a look in our system. How many links has a connection with ground? We have a moving links OA, we have a moving links AB, and we have our piston moving links, correct? And now look at here. Our OA, the crank, is connected or secured against the engine block. So engine block is a ground because engine block is not moving, correct or not? So therefore, it is our OA link to has a connection with ground. Clear to everyone? And our OA's velocity is which one? Our VA. And VA should start from the origin of the vector polygon. You see how we identified? We identified which link has a connection with ground and their parameters here. Clear? And now we go to the right hand side. Our piston B is restricted by who? By the cylinder wall. Cylinder wall decided how the piston will be moving. Correct or not? And our cylinder wall is moving? No, it is the engine block. Correct or not? So it is the ground. This section is the ground, this one. Right? So therefore our piston is sliding on the ground. Correct or not? So therefore our piston velocity, BB, this one also should start from the origin. Should start from the origin. Clear? Not must, should. And now have a look. We have a connecting rod. Does connecting rod has a direct connection with the ground here or ground here? No. So its velocity should not start from the origin. It can start but should not generally. Clear to everyone? Okay. And then there is another point it said. The another point said the absolute velocity and acceleration with 1 letter index, they should also start from the origin of the vector polygon. So let's go to see how we have 3 parameters. Where we have a 1 letter index, we have a 1 letter index of VV, we have 1 letter index of VA. This is a 2 letter index. It is not a 1 letter index. And this one is called absolute velocity, this one also called absolute velocity. This 2 letter index we call relative velocity. Correct? We call relative velocity. Not absolute velocity, relative velocity. So therefore, we said everything very nicely. Everything is said there. They said, so that means this one has an absolute velocity, this one is absolute velocity. Even you can sometimes forget, that's why I said 1 letter index. So our VV and our VA should start from the origin of the vector polygon, it says. BBA should not. But there are some exceptions. We also will be having a problem tomorrow. We'll show you that it will actually have some exclusion, but that is very rare. So that is not our main business. Main business is this one. Clear? And young people, I request you, if you go through this way, graphical method will be one of the easiest method and one of the finest method. You will be always be proud of that you know these things and how complex. You do not need any complex tool at all. I'll also show you that things how you solve it so quickly. Okay? So let's go down. Our equation says all parameter direction must be known. So we'll be asking two questions, each of these parameters. Two questions. We'll be asking two questions. One question will be asking directions, about its direction. And one question will be, second question will be asking about its value or magnitude. So let's go to start first question with our VA. So we ask VA, do you know its direction? We know its direction. How it is directed? Because our omega is clockwise, so therefore our VA will be going this way, correct? If omega was anti-clockwise, our VA will be reversed that way, like your assignment. Your assignment, your VA is going opposite direction this way. Why? Because your omega is rotating anti-clockwise, that's why. And here is a clockwise, that's why it is going this way. Clear, everyone? Because our VA direction is determined by the omega, rotational velocity. So now our VA, we know its direction. It is perpendicular to OA. And that's why the first underline, the red underline I put, and then I wrote with the red color perpendicular to OA. Can you see that? There is a signal. It is not that I liked it and that's why I put it. No, it has a meaning. This line has a meaning. The first line means you know its direction. How it is directed? Perpendicular to OA. You see the symbol perpendicular 90-degree angle? Can you see that? Here is the OA. Directed perpendicular to which link? OA. So we wrote here. And the second question I will be asking, do you know its value or magnitude? Yes, because its value is omega 2 times ROA. Its value is 100 millimeter per second or 0.1 meter per second. Yes or no? So therefore we will be putting second underline. I put a different color, black color. I did not put the same red color because I wanted you to understand it is not the same thing. This first underline means you know direction. Second underline means you know its value or magnitude. Clear? It's a very universal standard. It is a graphical method. It's a very powerful method. Very powerful method. And one of the important thing, I give you an example because I come from aeronautical background, that's why. And my master's specialization is a helicopter. So in a helicopter, you have a helicopter, that little tail, right? Normal. And then, because when you have one propeller is going on propeller, it means one set of propeller, 3 blade or whatever it is, there, it has a gyroscopic moment, so it will try to rotate some other direction. So that's why you need to have another propeller, small one, in the tail, so that it can balance it. Clear to everyone? Otherwise, helicopter will be rotating like that. So therefore, what happened? The tail is coming, is there, and then there is a little things where propeller you are putting here, small one. So this connection, so this one and this one, you cannot connect. That joint should not be rectangular, should not be is a very sharp because it's a lot of stress there. So it need to be very nice way to move this way, and that you cannot do in a normal calculation. So how the stress will be distributed so that it will not be concentrated in the joint. Clear to everyone? So that's why we are using finest way graphically to have this connection, these things, and then we replicate it in our manufacturing system, because we don't want, when you create the joint such a way, because it is not a pure straight line joint, it is a little bit of curved joint, so that our stress can distribute without concentration on any of the section of that joint. Clear to everyone? Otherwise it will be disintegrated, and this disintegration means the helicopter will be crashed. Helicopter, no way you can save it, it will crash. And that is still done by graphically. by graphical. So graphical method is a very robust method. Okay, so what we know about that, we find. And then we move on to here. Have a look. VBA. Do we know VBA's direction? All of you now is scratching head. This one is clear, VA, but this one not clear. And how it can be clear? Go back to our previous our Bible. Here, have a look. We found our VBA is a 90-degree angle or perpendicular to AB. Can you see that? If you did not do this synthesis, you will not be able to say it. And I also made a small comment. I'm not sure how many of you actually noticed about it. I said all relative velocity with a 2-letter index like this, they are perpendicular to their respective link, and we found from here. So therefore, but one good thing is, we see that our VBA is going upward, correct? But we do not need to say whether it is going upward or whether it is going downward. Our vector polygon will tell us exactly what is going on. But only thing we need to say that our VBA is a 90-degree angle of AB, and that is more than enough. Clear to everyone? So now we say yes, we know its direction. Its direction, we are saying it is a perpendicular to AB. Look at here very carefully. I'm not saying that it is going up. Can you see? We'll see our graphical method what it says. Because we synthesize the mechanism, that's how we know it is going up. Clear to everyone? But what our graphical vector polygon will tell us exactly which way it is going. We don't need to go back to synthesis. But only thing we need to say, it is a 90-degree angle of AB, perpendicular to AB. That's all. Now have a look, young people. Second question I need to ask, do we know its magnitude? We do not know its magnitude. Why? Because we do not know omega 2 as for omega AB. Look at here. Look at here. Because this VBA equals omega AB times RAB. RAB we know, 400 millimeter, but we don't know omega AB. Therefore we cannot find its value or magnitude. Clear to everyone? Our RAB is known to us, 400 millimeter, but we don't know omega AB. We do not know omega AB. So that's why we cannot do it. Clear? Okay, so let's go to here. So therefore, young people, you can see I did not put my black underline here. Can you see that? I left it. I left it here. I did not, because we don't know value. So that's why I only put the direction one. And now I am coming back to the left hand side. We have a BB. Now look at here very carefully, young people here. When our OA is coming this downward, our BB should go to the right. Correct? And when our A position is somewhere here, our BB will be going this way. So it will be going here this way. Forward, backward, correct? Horizontally. So we say yes, we know its direction. How it is directed? Horizontally. And horizontal, what is it? X and X. So I am writing parallel to X and X. Can you see that? If it is going vertically up like that, we say parallel to YY. If it is a 3-dimensional in the Z direction, you will say parallel to Z, but R is a 2-dimensional. And now, do we know its value? No. We are looking for it. That is our question here. What is our BB? What is our BB? We can find it. So that's why, now have a look. I cannot put a second underline. Second underline is not there because we don't know its value. That's why. So we know only one parameter value there. And you see, in our one of the point was some parameters value should be known. Remember I said yes or no? And we have one parameter value is known to us. So we ticked all the boxes. And now, if you look at very carefully in this equation, you can see we have 3 parameters. Every 3 parameters has a one common thing. What is that? Red underline. Can you see that? And red underline is your directions. So it means all 3 parameter directions are known to us. So we tick that box as well, because we say directions of every parameter must be known. It is not even should be, must be. So here we also have these things. Clear to everyone? So we tick that box as well. And now we are in a position to start our constructing vector polygon. If you do not follow this grammar, you do not know graphical method. If you do not do this grammar correctly, the way I do, you cannot do. Because I can twist your head. In the exam, when I put the problem, you will not be able to do the problem because you do not follow the correct procedures. And the way I explained to you, if you remember these things and you follow this one, first of all, you will not forget. Even you, after sometimes you looks like you forget, but you actually not forget. When you see this note, immediately you recollect your memory. Clear to everyone? Because the way I have written, I written that so that you can remember, you can understand, and I did not write what is in the book. Because this subject I teach from my head, I do not follow, I do not look at the book, how the book is done. Because I saw in the book, I was horrified. I was horrified. That this way, we cannot teach our student dynamics. Because they will be losing interest, and they will be afraid, they will be fearing it, they will be scaring about it, and they will be not putting their effort. Dynamics is a beautiful subject. So does the solid mechanics, so does the thermodynamics, so does the other fluid mechanics. They're all beautiful subjects, but we need to understand it. That's all. Okay, so now we are in a position now to plot the vector polygon to solve it. So what do we need to do? We need to select a scale. And this one, remember I said that this one needs to be plotted in scale. So this scale, it means it should be 400 millimeter. Proportionally, this OA will be 100 millimeter. Our AB should be proportionally 400 millimeter, and our angle should be 45 degree. Clear to everyone? If you draw this one correctly, subsequently you don't need any more compass. You just need a 2 ruler. If you draw this one correctly, you do not need to use any more compass. If you use compass, you are doing wrong thing. I'll show you now. I'll show you now how we do it. So let's go to. We already know all these things. That's good. And here, I put the equation again so that you can see. Okay, young people, because otherwise it is difficult to go one page forward, one page backward. I don't like it. So that's why I put it again for you. What are the things there? And now this is our position. And first of all, we need to put our scale. So we have our BA. Remember, BA equals 100 millimeter. And always another important tip I give you. When you select this scale, do not select any scale such a way so it comes some fraction point. Clear? Do not select that 15 millimeter per second equals 1 millimeter in our graph paper. Then it will be fraction. Clear to everyone? Because the fraction when we draw, it will disappear. You cannot draw them correctly. 0.2 and 0.5 you cannot differentiate. As a result, it will introduce error. It will introduce error. Graphical method is a fantastic method, but you need to be a little bit careful few things. So for example, if I do 10 millimeter per second equals 1 millimeter in our graph paper, then this 100 millimeter of our VVA, millimeter per second, will be only 10 millimeter length. Clear to everyone? But 10 millimeter is very tiny. So when you select, you do such a way so that you can fit within the page. Clear? Ideally, when I did, we used not A4, we used A3, the bigger one. So we draw everything as big as possible, and then we can, so that error we don't have, because we try to avoid the fraction, decimal point. So now have a look, but for simplification we say the 10 millimeter per second equals 1 millimeter per second, 1 millimeter in our graph paper. Okay, so, and then it says you need to select an origin. Or the origin, what is origin? Origin is the starting point of the vector polygon. Starting point of the vector polygon. So now look at here. What I did, usually my advice to you, take always the starting points in the paper middle point. Do not take on the side, because you don't know which line will go which way. Clear to everyone? So that's why that starting point always take in the middle of the paper. If all the paper is empty, you put in the middle that starting point. Then it will be easier for you to navigate. Otherwise, you have to redraw it and wasting your time. So now we assume that is our starting point, and that's the origin. So now we have this equation, our BBA, BB, BA, and BDA. So which one will start first? Which one you know the value? Value you know VA. And therefore, and how the VA will start? From where it will start? It will start from the origin. Why? Because our VA is the velocity of a link OA which has a connection with ground. And other thing, it has also absolute velocity, one letter index. Therefore, it also should start from the origin here. Clear to everyone? So what I will be doing? I will be taking a little ruler. Little ruler is that a 90-degree angle paper. Look at it, I show you these things. So if I go there, from here, I put it there, and then I bring it. For example, if I show it here, look at here. There is any eraser over here? No. So look at here. If our crank connected piston mechanism is here, if this one here, and look at here how I will be doing. Our VA, I'm just showing, it's not proportionality because it's a different there. So our VA, this is our VA, 90-degree angle, OA, and our VB is going this way. So how I'll be doing, look at it. I will be putting the origin here, and then, that's why I don't like PowerPoint. So look at here, I'll be doing, because I think he's definitely I'm sleeping. So you need to put, because I did not follow properly. So that is your VA, a 90-degree angle. So you can see it will be more or less, look at here. Even without using your compass or everything, you can see it is how very close to the 90 degree. Can you see that? So now you want to bring it here. So look at here, you put this space, and then you put this space here. You put it here, and then you put this one, put it here, and that is your 90 degree. Can you see that? I think I do this from this side, many of you did not see it. And this side they saw it. I do it again. Because you, unfortunately, many of you did not do that drafting. That's why it's been a little bit harder for you. So look at here how I do. This is my, say, 90 degree angle. I draw these things in scale. That's the thing you need to make sure. So now what I do, my objective is to bring that one parallelly here, right? So I put it here, look at here. I put this one here, and then I put this one here, and then I put it here. You see? How many minutes it requires? Very little, few seconds. But if you try to plot it in 90 degree angle, all of these things using your compass, it will take about 10-15 minutes. And I do within few seconds. So that's how we'll be doing. That's how we'll be doing. So I bring it here. So, and it is how many millimeter? 10 millimeter. So say it's a 10 millimeter here. Look at here how I did. That is the length of 10 millimeter. Where it finishes, I finish an arrow with that. Do not put arrow in the middle. Because if you put in the middle, it shows direction. It doesn't show the magnitude. But here, this arrow, it shows the direction and the full scale of the 10 millimeter per second. Follow the grammar. And now, I nicely write VA perpendicular to OA. What are the things I have written there? And now, the second parameters is our VBA. And where our VA finished, our VBA will start from there. That's as per our equation. Look at there. As per our equation. So I take out these things we don't need anymore. So now, as per our equation, look at here. Equation says where our VA finishes plus VBA, right? So from the tip of VA, our VBA should start. But how it will be directed? It will be directed perpendicular to AB. So look at here. So our VBA, I write down the equation for you because very difficult to see. VA plus VBA, that is our equation. So now, look at here. Our VBA BBA is a perpendicular to AB, and this one is a perpendicular to OA, perpendicular to OA, and this one parallel to X and X. That is our direction. And of course, we have another line, magnitude is known to us. That's our equation. So look at here how I get it. And it is 90-degree angle of this AB, right? Look at here, 90-degree angle, right? So what I'll do, I put 2A, that 2 times, then you can see it. Look at here, young people, how I bring it here. And then I bring it here. Can you see how I brought? I'm showing it again here, those who did not see from this side. So it is your 90-degree angle. I put this one here, and then I bring it here, and then I bring it here, like that. So ruler you can put in this parallel. Clear to everyone? So what I do, I am now putting a different color. So our is a perpendicular, so I put here. But I do not know whether our BBA is going downward or it is going upward. But it will start from the tip of BA. That's the things we know. Our BBA should start from the tip of this. If you don't follow this one, you will make mistake. You will make mistake and you will not do the correct thing, because your assignment problem you solve, because that you solve at home consulting with your fellow students, and you are doing very good in it. But if I give you a problem in the exam, and there will be in the exam your problem definitely, and if you don't follow the grammar, you will not be able to do it correctly. So that's why you see how I did, because that one our BBA start from the tip. That's as per our equation. But whether it is going this way or that way, we don't know. That's why, and also I put a dotted line, not continuous line. Why? Because we do not know its value. We only know its direction. So direction means only that our real value will be on this line somewhere. So now nicely I say this is our BBA. It is a perpendicular to AB. Perpendicular to AB. Clear? And now have a look. So we finish our right hand side. We do not have any more parameter right hand side. 2 parameter we plotted there. And now we have a last parameter, our BB. And the BB, from where should it start? It cannot start from on this line. Why? Because we don't know where it actually finishes. This one we knew it finishes here. That's why our BB we could start from the tip of BA. But we need to look at our BB. It's the velocity of a link that has connection with ground. Therefore, it should start from where? From the origin. And the origin you always put little bit of circle type things, so that you know from where it is started. So now our BB should start from the origin, but from the origin it can go to the right, it can go to the left. It can go to the right, it can go to the left. But how it will be going? Parallel to horizontal direction. So what I'll be doing, I'll take this paper again. That is our ruler. And this is the beauty. Graphical method, you don't need a computer. You don't need anything. You can, on the production floor, you can stand on the paper and you can immediately solve the many things there within a few seconds. No other method will give you that method, that convenience. So now have a look. Check it there. Look at here. Parallel. Hey, young people, you can put another one here, another one there, and you can come up to that point. You can clear to everyone, because this is a 90-degree angle, and it is cut in the factory, more or less accurate. So now, what I will be doing, I will be taking this one parallelly. I bring here, and I put in the origin, and I will be drawing a line. So now, let's go to line, draw with the red color. So, because our BB should start from the tip here. It can go to the right, it can go to the left. We don't know at this moment. We'll find out what our graph, although we see that our BB is going that way, but we don't need to worry about it at this moment. Because if we only worry on that, then we make mistake in our acceleration, you see in a second. So now what I do, look at here, I draw a dotted line like that. It is coming from the origin, and I say here nicely, that is our BB's direction parallel to X and X. Can you see, young people, how I did? So our BB, that BB should start from the origin. It can go to the left or it can go to the right, but it is parallel to the horizontal direction. Similarly, I did BBA perpendicular to AB. It can go up or it can go down. Clear to everyone? And now I am scratching my head. scratching my head, looking at this diagram. If I see that our BBA goes down and our BB goes left, it will never close the vector polygon. But our equation says they have to close. Yes, everyone? Equation says they have to close. So to close these things, our red line, which is BB, should come to the left, to the right, and our BBA should come to the upward. Then can intersect there and close the vector polygon. There is no other way. But our equation says they have to close. Can you see that? So therefore now I say, aha, I found the bingo. How? I can say now, look at here what I am doing. Because that is the interesting point. They intersect, right? So now look at here how I do. I will be taking from here this dotted line. I will be making now continuous line up to which point? Up to this point. And I finish my arrow. And I finish my arrow. From here, dotted line now become continuous line, and this is my real length of BB. My real length of BB. And now I am coming to our BBA. From here, it can go all the way up to there where the red line, and that I finish with arrow. And that is my real BBA. And look at very carefully. This dotted line I left, this dotted line I left, this dotted line I left, this dotted line I left. Because I am not a god or not a superhuman. I have no clue which way my BBA is going, which way my BBA is going. I only looked at as I draw, and I looked at analyzed equation, and then I did it. If I do not see that things is done in the test or in the exam or in the assignment, I will ask Dr. Chanda not to mark at all, because that person memorized. That person memorized, did not follow the right rule. How do you know your BBA only this one? How do you know your BB is only this one? How? Tell me. No way. Until you do these things. Clear to everyone? Because you will be neither God or superhuman, which is not possible. Neither of them possible. That's the things I want from you young people. Follow the grammar. You see how I did? I left the dotted line. That is unnecessary. This is unnecessary. From here up to there. And now what I will be doing, young people? Take that length. How many millimeter? Multiply with our scale. That is there. Clear to everyone? We get the value. And I measure with the ruler this one. What are the things I need? Very simple tools. Ruler and a couple of rectangular things. Do I need any even compass we don't need. You see? It will take few minutes if you do by yourself. And now have a look. Now have a look. Young people, have a look very carefully. Our BBA, when I synthesize the mechanism, which way our BBA was going, let's go to have a look. Let's go to have a look. Let's go to have a look. Look at here. Which way our BBA is going? Hey, young people, our BBA is going up. What is going on here? Our BBA also going up. So how accurately we have synthesized, and how accurately our vector polygon is saying these things. You see that? All puzzle is coming together. If you cannot bring together, it means dynamics is not, graphical method not in here. That is the thing. I request you to look at that. That's why I said that is the Bible. Because you will be comparing everything against it. And look at here. Our BB also going to the right. And our BB also going to the right. Although I see it is going to the right, but I did not guess. I follow the grammar. I follow the things, and then I saw how I did it. So this is the things young people you know. Clear to everyone? Okay, now we'll be doing acceleration part. So what I did, a little bit, have a look. So we did everything, and then what I did, I took the how many millimeter that length, and that is our length times the scale. It will be millimeter per second. That scale is a 10 millimeter per second. Remember your scale, and then VV, that length multiply with the scale, you get this one. And then what is our VBA? Look at the equation. R omega AB times RAB, and from here now we are finding the omega AB, the connecting rod rotational motion. Clear? Remember that? That's how it will be. So I can twist your head. I can say, find out the omega AB. I'm not saying anything, but you cannot find it until you find these things. Clear to everyone? That is your process. That is the process. So I really want you young people, you follow the rule because discipline, follow rule is very important. And as I said, graphical method is one of the easiest methods. Now you are doing your assignment, you already know that it is so easy compared to your analytical method. Analytical method is very hard. Even the equation you saw that how difficult to do all this equation, and then there is a big possibility you make mistakes somewhere. But graphical method, nothing can go wrong. Nothing can go wrong. Absolutely nothing. Because you draw only 3 lines. You can easily see which one is wrong or which one is right. Clear? Nothing can go wrong. But you know you are doing now analytical part. Look at there how hard it is. Where you made mistake, only God knows. To find it very, very hard. Isn't it? A small, tiny parameter you missed somewhere. And you will be struggling a lot of time. But graphical method, these 3 things, what are the things will go? Nothing. Okay? And now we do acceleration part. And after that, I think, when will we have to finish, young people? Today? 10:30. So what is the time? We are, where are we now? 10 o'clock. Already? Oh God, we need to go with the speed of light. Alright. Before I go to the acceleration part, I want to, because I am not 100% sure how many of you actually know normal and tangential coordinate system very well or not. Okay, because you have done some time ago, at least 1 or 1.5 years ago, right? When you did your engineering dynamics course. Young people, you remember?
1 year.
I don't know, at least 1 year, or maybe more, correct? So, because my son, he finished last year high school, and now he's at university. He already finished first year. So when I asked him something, he said, "Oh, Dad, we did it 1 year ago. We forgot." So I didn't ask anymore because I know that if I ask something, then father and son relation will be very bad. So it is better not to ask. I just keep mouth shut. Okay, so young people, you learn in high school something or university something, not to forget everything. Few things you need to remember. Okay, that's the most important. Of course, you will forget some. All you don't remember all of them. Definitely, particular formula you will forget. So now the question is, I am not 100% sure because as I did not teach that subject to you, to teach you, it means I did not do the course review workshop with you. That I mean, because unfortunately our Melbourne academics, they come only for course review workshop. So this is why I want to make sure that you understand the normal and tangential coordinate system very well. It is one of the widely used system we use in our engineering application. So now let's go to explain this one here. Because I draw all these beautiful things, maybe it is not very nice, but when I explain there, it will be more easier for you to understand. So now where is that things I put here? Have a look. I keep this one, we need it. So I take out this one and I explain here. Look at here. If we have a curvilinear path, say a car is moving, but in Singapore is predominantly flat. So if you're moving like that, you have something, right? And we call curved path. It means it's not a straight line. So consider that is a curved path. Look at here. And then some section is a straight line path. So this is our car is moving on this path. It is moving from left to right. That's why I showed the arrow this way. Clear to everyone? It can go also opposite direction as well. So now have a look, young people. We want to use our normal and tangential coordinate system only can be applied for a curved path, not for a straight line path. Clear to everyone? Only when motion has not straight line but a rotation of a curved path. Now the question is, we have a two component, normal component and tangential component. It is mainly for acceleration. Velocity we don't split. Velocity we do not split, velocity only one. So now, what do we do? If you look at very carefully, although each of the sections looks like very complicated, right? So now, each of this section we can make a little circle. Look at here. We can make this one a little circle. Look at here. A little circle, although not 100% circle, but close to. And then have a look. This one, we can also make a little circle, although looks like an egg, but very close to very circle. And then if you look at here, and this one also, and so on. So we make it approximately circle. Okay. So now have a look. So when our particle or a car is somewhere, say here, at that location. So when this at that location, this arc is a part of this circle, which center is somewhere here. This is the center of the circle, and this is the position of the vehicle, motorcycle, car, whatever it is. So now, the normal and tangential component, first it says, first locate where is your vehicle or point position on the path, and this is our position, we found. And then using that section, make a circle, which is I made a dotted line of the green, the blue dotted line. Correct? And where is its center? Center is here. Can you see that? Center of that circle. And then it says, from the position you draw an coordinate system towards the center of circle. Now look at here. From the position towards the center of the circle, your n coordinate system. That must. And then 90-degree angle of that will be your t coordinate system. Your t is this one. That is your tangential 90-degree angle. Now, that t will follow at the moment it is moving from left to right. That's why our t is going to the right. Clear to everyone? And if our car or particle moved from right to left, our t will be 180-degree opposite. Clear to everyone? Still 90-degree angle with the n coordinate system. But n coordinate system direction will not change. It will be always directed from the center to the, from the position to the center of the circle. Clear to everyone? And now, in the direction of the n coordinate system, we direct our an, and in the direction of t coordinate system, we direct our at. Clear to everyone? In the n coordinate direction, it will be our normal component of the acceleration. In the tangential direction, the t direction, will be our tangential component of the acceleration. Clear to everyone? And now, if both of them are there, some value, they can be equal, they can be different, doesn't matter. So you can combine a parallelogram, and then absolute acceleration will be this one, is A. Because two vector, you make a parallelogram, you made a diagonal, and diagonal is your absolute vector. Clear to everyone? And now look at here. If you do not have AT, then you have only AN. And AN will be your A. A will be this way, right? If you do not have AN, you have only AT, then your absolute A will be in this direction. Correct or not? Please analyze these things. Very important. So now look at here. Let's go to see here when our particle is here. So now this is our center, and our particle location is here. So from here toward the center will be our n coordinate system, and perpendicular to it is our t. You see, I follow the grammar. I don't follow anything. I do not look at anything. I first look at where is our position, where is our center of the circle. from the position to the center of the circle will be n coordinate system. I will be always drawing first n. I will never draw at t. If you draw first, that is the wrong thing. Because you need to first identify where is the center of the circle and from where is our position of the curve. And from the position towards the center will be our n coordinate system. That is the things. It is not written very well in the book, but you follow this way, and you will not make mistake. You will see later on why it is important. Why it is important, you will see later on. Because otherwise, it will confuse you, and you will be memorizing. And our engineering, we don't need to memorize anything. We need to understand it. And to understand it, young people, the way I explained, that is the easiest way to remember, because I remember these things for last, for how many, 1985 I finished, and now how many years already? Long time ago. Isn't it? So 1985, next year will be 1984. So is it how many years? 38 years, right? You see how? That's how I remember. Because I follow the grammar. I do not follow anything. Believe me. And I also done all these things in other languages, not even English. And I am explaining to you English. If I did not understand in depth in the other languages, I would never be able to say it. I will never be able to say it. So now, that will be our AT in the direction, and this direction will be our AM. Yes. In the direction of M, in the direction of T. So it will be following this way. Now, young people, I write down a formula, and then I'll ask you a couple of questions. Now, our AN by formula. AN equals V square by radius of curvature. The rho is the radius of curvature. If the object is moving fully circular path, like our OA, then radius of the curvature, rho become R. Rho become R if it is a fully circular path. I am also writing for you. If fully circular path, I'm moving on the other direction so you can see, then rho becomes R, radius of the circle. Clear to everyone? If not, rho is not R. Rho is a different value. Rho is the different value. Please note about that. You don't need to memorize anything. You did it in your engineering dynamics, but you most probably forgot. So if fully circular path, then rho equals R. If not, then rho equals never R. There are something else. What is it? I'm writing. Then in that case, you need to know mathematical equation of the path. If the path equation is, I'm writing, if path equation is, say, y equals fx function, whatever it is, in that case, you can write rho equals 1 plus dy by dx, all these things is squared, this is a 1, and then you put the whole to the power 3, and then you put a square root divided by d square y by dx square in absolute form. That is the formula. In your dynamics, how many formula you have? All the formula is in my head. Not only dynamics, in solid mechanics, in fluid mechanics, thermodynamics, all these things. Because I have a very photogenic memory, that's why. You don't need to memorize this formula, because it's extremely hard for you to remember. Now you can ask me okay, Professor Firoz, how you remember these things? Because I remember like a telephone number. I never try to memorize any equation without a telephone number. If I ask you your mobile number, how you say? Most probably you say first 4 digit and the remaining 4 digit and remaining 2 digit or something, correct? But do you say at one go all number? No. That's exactly the same thing I do. Okay? Now, that is our formula. And what is our AT? Our AT, because I need that one. I need that one tomorrow a lot. That's why I'm spending time. There is a reason for that, young people. It is not that I want to take you back 1 year back. No, that is not my intention. I want to bring from 1 year here now. Because I want that your knowledge from 1 year ago, what you learned, we need to apply in this course. Because some of the course, that's why I'm now doing these things for you. So our AT equals dV divided by dt. If V equals R omega, because that's we did it in the formula, divided by dt, and our R will be in the front, d omega by dt, it is actually angular acceleration, R alpha. All these things you learn in your engineering dynamics. And now my question is, young people, that is clear. And absolute form, our A equals square root of A n square. I finish this one and after that we will stop because we will not be solving the acceleration one, we will do it quickly tomorrow. So, but I want to this one because we need that one, otherwise you will not understand when I will be doing all these things. So, our AT is square. Now have a look, young people. I want to draw your attention on one thing before you go home. This section is our straight line path. Correct? Look at here, this section from here. And anyone can tell me what is the radius of curvature here? What is the rho value here?
1.
And you also look at your formula as well. You understand my question? My question is, our car was moving on a curved path and all of a sudden there is a flat path like that. And that flat path is at the end. So what will be our AN there? And what will be our rho there? You got my point? Is it clear to everyone? The question that I am asking. Consider that our car is now moving on the flat path. So, and flat path, what will be our AN? What will be our AT? And what will be our absolute A? Anyone can tell me?
0.
This young man says, look at here. This young man says, he's a brave man. First of all, I need to praise him because he's telling rho equals 0, he said, right? And some of you, do you agree with this young man? He said rho equals 0. Now let's go to have a look. One person says something, but I'll come to that point in a second. So now look at here our formula. Hey, young people, the formula is in front of you. If you put in this situation rho equals 0, v square by 0. V square by 0, it means anything divided by 0 is infinity. Can it be possible? Billion, trillion, kilometer per hour per second square and acceleration. Infinity, it means there is no end of it, right? That's what infinity means. Yes or no? There is no end of it. It cannot be. So therefore, we need to write what? We need to write, this young man correctly said, we need to write infinity here. Why? Why infinity? It is not that I want to put it here. The reason is that small section straight line path looks like, when we are looking from close, looks like it is a straight line, correct? But if I take my step back, I'm looking from other side, it is actually little curve, but I cannot see it. Like our planet. If you look at from Melbourne, when I came to Singapore, it is actually not a straight path. I saw I'm in the bottom of the world, I came like that. But when I'm in Melbourne, can I see I'm a curve? No, I see flat path. All are relative. All are relative, young people. Nothing is straight line, it is a relate. So therefore we say yes, there is a radius of curvature, but not here, infinity distance away. And that's why we say rho equals infinity. Clear to everyone? And now I am coming to mathematical equation of that. So young man, clear? If you, now look at here again. If we put here rho equals 0, then our AN becomes infinity, which is not possible in this world. So therefore our second option is, as this young man suggested, put infinity here. Rho equals infinity. So if I put the v square divided by infinity, anything divided by infinity equals 0. Correct? It is possible. It is possible, but not other one. So if I put the v square divided by infinity, and this becomes 0. Correct? And now have a look. Look at this equation. So your AN becomes 0, 0 is square. Your A equals AT. Can you see that? It becomes now one dimensional. Instead of two-dimensional, it becomes now one-dimensional. And all straight line path is a one-dimensional. You have only one acceleration. Correct or not? You see how everything coming nicely? And I really like that you young people, if you analyze this way, you don't need to memorize anything. Dynamics will be in your head. Okay, so I appreciate this young man who said 0, and who said also the other man, he was not very 100% confident, but I heard that he said infinity. Both of you are the right direction, you say. But of course, one is we cannot put it because it is not acceptable in our engineering application. Because it cannot be infinity. Otherwise, we cannot design any machinery, anything to sustain such a high acceleration. Clear? Okay. So with this note, I stop for today. And now, any one of you missed the attendance because I will be now confirming it.